Hello everyone, this is Varun. Welcome to Aerospace Structures. Now, today we are going to discuss about the principle of minimum potential and Rayleigh method. Let us go ahead. Okay, this is a schematic of a potential energy with respect to displacements. And the variation in potential energy of a system is zero. When you take any linear elastic system, the variation in potential energy is zero. It is not in the case of only the solid mechanics, but when you take any system, the system always tends to move towards the lower energy point or the lower potential. For example, when you take a water and when you spill it, what happens? It spreads all over the floor. That means it is minimizing its potential. And similarly, that is the quantity does not vary when virtual displacement is imposed. And moreover, the principle of superposition or the principle of minimum potential energy doesn't vary in the presence of the virtual displacements. This is a schematic of some arbitrary function. Let us say we have plotted pi of u. Pi is defined as a total potential of a system, which is defined as the strain energy minus the external work done is defined as a potential. And when we draw the potential on the y-axis and the displacements on the u-axis, the graph tends to be either at local minima or local maxima. Let us say u1 be the displacement at minimum point and u2 be the displacement at some other point, and delta u2 and delta u1 are the virtual displacements of a system. Okay, and what we can draw the conclusions from the following plot is that the total potential energy attains a stationary value at actual displacement ut. That is, for any given function, it attains a minimum value, and delta phi equals 0 for incorrect displacement. That means if we have a correct displacement, we have del phi, that the variation in potential is 0. If we doesn't have an incorrect displacement, and del phi cannot be equal to 0. And the potential energy due to applied load can be written as delta V. Let delta be the minus delta W external. That is the work done by the external forces. And finally, del phi can be written as delta U, the strain energy of a system plus the potential the total potential can be written as the strain energy minus the work done on a system. The external load must be conservative, precluding from example of sliding frictional loading. And moreover, this force should follow the principle of conservation, and we need to include the other forces like friction and other things. Okay, now the following relation holds good. For example, let us take a function f of x, and we have incremented by delta x. What we can write is that f of x plus something like a delta x Fourier series, it's Taylor series, dou f by dou x, and the quantity f of x plus delta x minus f of x can be written as delta f equal to dou f by dou x into delta x. Let us say for clarity this is delta. Okay, and similarly pi of a plus delta u can be minus pi of a can be written as del pi, which is equal to the dou pi of u by dou u, this is u, and this is u, and this is del u. That is, here the variation with respect to the deflection. This is the quantity which is called as the variation due to the variation of the total potential because of deflection. And thus, for all possible displacement u satisfy the loading and boundary conditions. That is one of the most important thing. That is what it should satisfy, is that it should satisfy the loading condition and the boundary condition. One cannot deny the boundary conditions of a system. The actual displacement is which gives rise to stationary potential. When we have an actual displacement, what we have is dou pi u by dou u equal to 0. The problem reduces to the finding stationary value. And finally, what we have is that now the problem reduces to finding the stationary value, either the maxima or minima of a system. Okay, now welcome to Rayleigh method. And this is one of the approximate technique. For example, when you have a structure like this, or let us take a plate. Right now we are not considering the plate in our section, and when you apply a load in the transverse direction, we have a formula to deflect to find the deflection. But in realistic condition, the plate may not be rectangular or circular. It may be something plate like this, and moreover there will be a hole in this plate for some other reasons. And if you need, and it is applied in this direction, if you need to seek the solution for such type of complex geometries, then our direct methods are, it doesn't have any closed form of solutions. Finally, we rely on the approximate solutions, and Rayleigh method is an approximate solution of finding the deflection or energies of a system. And let us look into what actually this Rayleigh method. The Rayleigh method is an approximate method where given function is directly minimized without recurrence to Euler, EL refers to Euler-Lagrange equation. And now what we are going, that we are not using any Euler-Lagrange equation. Now we are directly minimizing the potential of a system. In previous slides, I have discussed about the potential of a system. To illustrate a method, let us consider the following function. Now what we have is that we have a function. Functional refers to the function of functions. We have a independent variable x and y, and this independent variable and phi is also a function of x comma y, and dou phi, which is function of x comma y, is dou x, and dou phi x comma y by dou y. If we have a system like this, which is a function of independent and also a function of function, and what we can write is that we can write j phi, it's from integral in a from s. It doesn't mean that it's a closed integral f of x ds. And here our main objective is to minimize the function j. And let us look what happens and how we do is that. Okay, in Rayleigh method, we select a linear independent set of functions called basis function un and construct an approximate solution. And what it is saying is that already we doesn't have any direct solution or any kind of closed form solutions. Finally, we need to rely on the approximate solution. And what this Rayleigh method is saying that we can express phi. Let us say it is delta phi because it is not approximate, in the form of some basis function which is given as u naught plus sigma I equal to 1 to n a n and u n. Pause for a moment. I would like to recall one of the concepts. You might have familiar about the Fourier series. And what Fourier series say is that the function f of x can be expressed as a naught by 2 plus sigma I equal to 1 to n, something like a n cos n pi x plus sigma I equal to 1 to n b n sin n pi x. And here what you have observed, the first thing is that if we determine the quotients a naught and a n and b n, any function, that is the function, some function f of x, can be expressed in the form of sine and cosine series. And depending upon the number n, the accuracy of defining the approximate value of a function increases. Here, I'm not going to deep into the Fourier series and all this thing. And here, what you have expressed is that you have expressed function in some basis, that is, in terms of some constants a and b, and in sine and cosine series. And don't we use this concept of in our Rayleigh method? Instead of using this sine and cosine, we can use some other terms like polynomial series of first order, second order, or nth order to define the basis function. Okay, what Rayleigh method is saying that if we have a function like this and we can express the solution in the form of infinite series, that is the approximate tilde represent the approximate equal to u naught plus sigma I equal to 1 to n, capital N, let it be ai, sorry, this is I and this is I, the index I and un. For one dimensional it is x, x, and this is x. For homogeneous boundary conditions, u naught of x equal to 0. For non-homogeneous boundary conditions, the u naught of x is not equal to 0. And finally, the unknown coefficients. If we know the unknown coefficients and our system is well defined. Now, what we do is that already I have expressed the phi in terms of un. And what you can also express as dou phi by dou x, and which is given as something dou u naught by dou x plus sigma I equal to 1 to n ai dou u I by dou x. When I substitute this in the following equation, what we get is that this j is only the function of a1 to n. And if we apply the concept a, that is dou j of dou I equal to 0. Already we know that the system attains a minimum value, and that is a stationary value. We can find, if we apply dou j by dou I, what we get is a system of linear equations. And let us look into a problem. This is the schematic of our problem, and this is one end is roller support and another end is simply support, and we have a moment m. The total potential of a system can be written as integral 0 to L ei by 2 into dy by dx whole square plus m naught y into dx. This is because of external work done, and this is because of strain energy, and the total potential energy as follows. And for this system, These are the following boundary conditions. When you clearly look into the picture, the deflections produced at the ends are zero. Finally, the exact solution for the given problem is given in solid mechanics, which is m naught divided by 2ei into x square minus lx. Now, what we do is that we rely on approximate solution. Let us say this is y tilde can be expressed as u naught plus sigma I equal to 1 to n a n and u n. Here, one thing I have said that if we determine the a n or a n and our system is well defined, but what about un? Let us look about this un and u naught, and this un and u naught will be can be expressed in the form of polynomials or in trigonometric series. And in the form of polynomials, what we can write is the approximate value of y equal to sigma I equal to 1 to n a I x I. And in terms of, if you like to express in terms of trigonometric function, you can express this as follows. And doesn't it look like Fourier series expansion? For a time being, we are considering the trigonometric series as n equal to 1 with homogeneous boundary conditions. Finally, what we get is y tilde equal to a sin k pi x for n equal to 1. And if we apply the boundary conditions, what we get is k equal to 1, and the approximate solution is y tilde is equal to a. This is a sine. It doesn't mean that arc of sine. It is not a sine inverse. A times the sine pi x by n. And a is undetermined parameter to be found out. If we found the undetermined parameter, that is a, then our solution is complete and we can use it for practical purposes. We have to select such that the function y is minimum, substituting the above approximate. That is, if we substitute the following equation in the given equation, and we apply the formula dou phi by dou a equal to 0, what we get is that we get the approximate solution of y of x. Simply what I am doing is that I am substituting this solution into this equation of y. Finally, without going deep into the algebra, you will be getting the following equation. And what we have is that now the potential energy phi of A can be expressed as EI pi square divided by 4L A square plus 2 m naught L by pi A. And if we apply dou phi by dou A equal to 0, finally what we get is the following formula, and A equal to minus 4 m naught L by pi EI. And now if we plot the exact solution and the approximate solution, this is the plot. What we get is, and you can see how accurate with exact, and this can be applied to the other concepts, and you can also use the series expansion technique. And thank you very much. This is Varun signing off.
Like, share and subscribe. Hit the bell icon for more updates.